um, compound probability. And so it's doing a lot of the things that we did yesterday, but we're going to do it with multiple events. And so yesterday it was just like, what's the probability of rolling a die and getting whatever outcome I wanted? Or you can do it with any event. But today we're going to do multiple events. What if I rolled a dice twice? Or what if I picked two cards out of a deck of cards? Or something along those lines. And so we call that compound probability. It is the probability of two or more events, whatever those events are. Okay, lots of different scenarios. Just trying to do two things or more than two things. And the two things could be on the same item. Like, for instance, I could take a dice, I could roll it, and then I could see what I get, and I could roll it again, right? If I was picking from a deck of cards, I could reach in to a deck of cards, I could pick a card out, and then I could reach in and pick another card out, okay? So it could be from the same thing, or you could also even think of something like roll a die, then toss a coin. So two completely different events that don't necessarily have anything to do with one another, but I can find the probability of two things happening. And I want both of those things to happen. Okay, so the first thing we're going to talk about is what we call an independent outcome. And so rolling a dice and tossing a coin are independent outcomes because one does not affect the other. If you say that you're an independent person, that kind of makes you your own person, right? You kind of go do your own thing and it makes you kind of who you are. It's your personality, right? And in this case, the two outcomes, if they're independent of one another, they are totally independent of one another. They don't have anything to do with one another. What I get on a die has nothing to do with what I get on a coin. Okay, those two outcomes are totally independent of one another. They do not affect one another. We talked the other day about the word and we're going to see that a lot. And I told you I'm going to really hound this into you that when we do probability, what do we want to occur? In this case, we want probability of something in event A and something in probability of event B to happen. And so we would read this as the probability of A and B. In order to figure out what that probability would be, we would take the probability of A times the probability of B, whatever that is. And there's a lot of different scenarios that could be given to us, and we're going to look at some examples of that. Okay, it's kind of like the last couple of days. There's a lot of examples here. We're not going to do every single one of these, but we're going to do quite a few of them, just so we can kind of get an idea of how this works. Okay, so on the first one, for questions 1 and 2, it tells me we're going to use the spinner to the left, and then we're going to pick a word, or pick a letter from the word bingo at random. So basically, if I took the 5 letters from the word bingo and put them into a bag, I reached in without looking and picked a letter out of the bag, I would have 5 letters to choose from, right? And so we want the probability of getting less than 7, then picking the letter B out of the bag. So we're going to do this event, and then we're going to do this event. So I'm going to spin the spinner, and I want to know what's the probability of getting a number less than 7. How many numbers on that spinner are less than 7? Don't think too hard. 6, right? 6 out of 10. There's 10 numbers on the spinner, 10 of them total. 10 numbers on the spinner, 6 of them are less than 7, I should say. So that's what we call like event A. That's the first outcome. Okay, event B is reaching into the bag and picking out something from the letter bingo. We got 5 letters to choose from, and I want the letter B. So there's only one way out of 5 that would happen. I got 5 letters to choose from, and there's only one B. So that would be 1 out of 5. Now, there's a couple of different ways that you could do this. Okay, we're going to multiply these two together. And remember, with multiplication of fractions, we do not need a common denominator. Okay, so the two options that you would have is I could reduce it first, and then I could multiply, or I could multiply and then reduce. Okay, it doesn't really matter. If you want your numbers to be a little bit smaller, you could reduce this by taking 2 out of it. So I would reduce 6/10 to be 3/5, and then I could multiply the two together, which is 3 out of 25. If I had multiplied them together right from the beginning, that would have given me 6 out of 50. 6 times 1, 10 times 5. And then I would have had to reduce the 6 over 50. And that would also have given me 3 out of 25. Okay. So it doesn't matter which order you go in. I kind of like the first way a little bit better, maybe, if it was me, because then you're dealing with a little bit smaller numbers, a little bit easier to reduce maybe when they're smaller numbers, a little bit easier to multiply. Okay. A lot of your calculators, if you took 6/10 times 1/5 in your calculator, it'll give you the reduced answer. So some of you might put that right into your calculator. And most of you have a fraction button on your calculator, and it might just give you the reduced fraction. Okay, we got to be really careful of wording here. At least 3. Does that mean we are including 3 or not? At least 3? Including 3 or not including 3? Including, right? So on the spinner, we have 10 numbers. At least 3 means basically everything except for 1 and 2, right? And so that would be 8 out of the 10 numbers. In the word bingo, how many vowels do we have? 2, okay? In the alphabet, you have either a consonant or you have a vowel. Okay, a vowel is A-E-I-O-U. Consonant is any other letter besides A-E-I-O-U. Okay, so we have I and O in the word bingo, so 2 out of 5 are vowels. Once again, and maybe try putting this into the calculator just to see what your calculator does with it. Try taking 8/10 times 2/5 and see what happens in your calculator. Carter, let's put your phone away, please. Okay, what do we get? Okay, 8/25. Okay, yesterday we talked about several different ways to write your answer. 8/25 would be fine. Okay, it doesn't really tell me how to leave my answer here. So I would accept any of these, like 8/25, 32%. We could also do 0.32 as a decimal, would be fine as well. So there's lots of different ways to express it. But probably typically fraction or percentage would be the way that we would go. Okay, on number 3, we're going to take a die, we're going to roll it 2 times. What is the probability of getting a number greater than 4 on both rolls? So the 2 events are independent, right? What I get on the first roll has nothing to do with what I get on the second roll. I could get the same number both times. So the first thing we know is that there's 6 outcomes both times I roll it, because we're rolling a die, 6 different outcomes. Okay, how many numbers on the die are greater than 4? 2. So this would be 2/6 times 2/6. And then however you want to do it, you could reduce it and say 1/3 times 1/3. And I kind of like reducing it first here because then the multiplication's a piece of cake, and that would give me 1/9. If you were to multiply it, you would have 4 out of 36, which just needs to be reduced. Okay, number 5. Towards the end of the lesson yesterday, I kind of gave you some different things about a deck of cards. We're going to see problems dealing with a deck of cards throughout this chapter. It's one of the most common things that we do with probability. What's the probability of a certain event happening, reaching into a deck of cards? Okay, and so on this one, the key word here is replaced. I reach in, I pick a card out, I put it back into the deck, I pick another card out. Okay? So I could get the same card twice. The likelihood of that happening would be very, very slim, right? Especially if I reshuffled the deck before I picked again. But I want to get diamond both times. When you do this one, there's a couple of different ways that you could think about it. In a deck of cards, how many suits are there? 4, right? You got clubs, spades, diamonds, and hearts. So you could do 13 out of 52 because there's 13 of each suit, but there's only 4 suits. And so what you could say is diamonds are one of the 4 suits. If I did 13 out of 52, guess what? It's still 1 out of 4, okay? And so we're simply just reducing it before we even write 13 out of 52. So we want the card that we picked to be a diamond. So the first card I picked, there's a 1 out of 4 chance that it's a diamond. The second card I pick, 1 out of 4 chance. Again, because I still have the same number of cards in the deck, and there's still a 1 out of 4 chance of that happening. And so that would be 1 out of 16. Okay, on number 7, an easier way to do this one, you could do a half times itself 4 times, because when I toss a coin, I got a 1 out of 2 chance of landing on heads. Or an easier way to maybe put that into the calculator is to take 1/2 to the 4th power. And that should be 1/16. So anytime you have something that repeats over and over and over again, you could just use an exponent as long as it's the same fraction every time. We kind of did one like this yesterday. Sometimes we like multiple choice tests because we're like, oh, I got a 25% chance of getting this right? But if I had 3 questions on the test, the last 3 questions on the test, I have no idea how to do them. And so I'm going to completely guess. What's the probability that I get all of them correct? Okay, what's the probability I get all 3 questions correct? Well, the first question, I have a 1 out of 4 chance of getting it right. Okay. And we're assuming we're just completely guessing. Okay, I don't have anything. If you kind of had an idea and say, oh, I'm going to eliminate B because I know B is not right, then that would help your probability a little bit. But if I'm completely guessing, I have a 1 out of 4 shot each time that I choose my answer. Or I could do 1/4 to the 3rd. Okay, whichever way you want to do that. Now, as I multiply these two to all 3 of these together, 1 times 1 times 1 is just 1, right? 4 times 4 times 4. 4 times 4 is 16. 16 times 4 is 1 out of 64. Okay. And that doesn't seem like a very good chance of happening, right? But let me show you. I think this makes a little bit more sense. If I put that into my calculator, your decimal would get you something like that. So we have about a 1.6% chance of guessing and getting those 3 questions right. Okay, so good idea to guess? Probably not, right? Not a very good chance I'm going to get those 3 right. Okay, and that's to get all 3 of them right. So sometimes we like multiple choice, but really in the big scheme of things, if I'm strictly guessing, I'm not probably going to do very well. Okay, number 9 up here at the top. Read through that little paragraph, and then we're going to talk about the probability of that. Darsten, let's pay attention. Wait, huh? Well, you got an AirPod in, you got your computer open, and you haven't even looked up here. So I don't really know how you're paying attention. It doesn't really look like it. You're not even on the right page. Okay, so we got 14 girls and 11 boys in his homeroom class. 9 girls and 15 boys in Mr. Jump's homeroom class. If a student is chosen at random from each class, what is the probability that they are both boys? Okay, and I just want to show you this. The way that this would be written out in words, because we'll see this sometimes, what's the probability that I would pick both boys? Okay, so that means a boy from Mrs. Haynes' classroom and then a boy from Mr. Jump's classroom. So let's focus on Mrs. Haynes first. If I was to choose a boy out of Mrs. Haynes' classroom, what's the probability that that would happen? How many kids does Mrs. Haynes have in her homeroom? 25. Okay. And out of those 25, how many of them are boys? 11. Okay, then we're going to go to Mr. Jump's homeroom. How many kids does he have? Okay. And out of those 24, 15 are boys. Once again, we can either reduce first, or on most of your calculators, like I said, and that's why I was telling you, when we get a little bit bigger numbers, most of you can go ahead and just multiply this. Your calculator is going to probably reduce it for you. Okay, so try putting this into the calculator just to see how your calculator does this and see how it leaves your answer. So you kind of know what you need to do to get your reduced answer. In most cases, your calculator will probably reduce it for you. Okay, what do we get here? 11 over 40. Okay, everybody able to get that in their calculator? Everybody kind of know where that fraction button's at? That fraction button's a pretty big help rather than using division. Okay, anybody need help with the calculator there? Okay, pretty nice little button that most of those calculators have to make things a little bit easier on you. Okay, so here we're going to still talk about the same thing, but in this case, this is dependent, okay? And so dependent event is where the first event that I do has affected the second event. And so a really good example of that is we go back to like the deck of cards. If I reach into a deck of cards and I pull a card out, I see what I get. Now, I'm not going to put that card back into the deck. Okay, I'm going to leave it out, and then I'm going to reach in and I'm going to pick a second card out. Well, the second time that I reach in, I started with 52 cards. I picked one out. Now there's only 51 cards left in the deck, right? And whatever card I had pulled out, there's going to be, like, let's say it's a 10 of hearts. Then we got one less 10, and we got one less heart as well. And so my first outcome has affected my second outcome. If you roll 2 dice, they're always independent. They're never going to be dependent, okay? If I have like a bag of marbles or something, and I reach in and I pick a color out, if I leave it out and I reach in and pick another one out, the first one has affected the second one. But if I put it back into the bag and reach in again, then I still have the same number to choose from, okay? So you're going to have to read these carefully. Most of the time, these problems will have no replacement. You're going to reach into something, you're going to pick something out, and you're not putting it back in to the mix, okay? And so you have one less to choose from the second time that I choose. The probability here, the first event hasn't been affected because you got to do the first event first, right? But then you're going to find the probability of event B happening after A has been taken out. So A has affected B. We're going to have less things to choose from. Okay, so here we are talking about this bag of marbles that I was mentioning a few minutes ago. Okay, so the first thing we need to decide is how many marbles are in this bag. $25, okay. So we got 25 marbles in this bag. Sometimes it tells me that, sometimes not. This time it doesn't tell me how many marbles we had. So I just got to add 3, 10, 4, and 8, figure out how many we got, okay. And then they're going to give me different situations. The first one says, what's the probability that I get a red marble on my first draw? So a red marble, there are 8 of them out of 25. So I have an 8 out of 25 chance of picking a red one out, okay? And then I want to pick a blue marble. Well, how many marbles are now left in the bag? 24, okay? Because the key here is what we talked about just a second ago. It is not replaced. I did not put the marble back in the bag. So now there's only 24 marbles left in the bag. And we still have all of our blue ones because the first time I picked out a red one. So we have all the blue ones to choose from. We multiply those two together. One over 25. Okay. So we got a 1 out of 25 chance of that happening. Okay, let's jump down to number 13. Both red. Okay, so once again, we got an 8 out of 25 chance. The first one is red. Now the second time we choose, if I keep the marble out of the bag, how many marbles are left in the bag? 24. And out of those 24 marbles, how many of them are red? Only 7, right? Because we picked a red one the first time, and now there's only 7 red ones left in the bag. And then we would multiply those two together. Here's kind of a trick, and I know your calculator does a lot of this work for you. As long as there's a multiplication sign right here, and I like to show you this because you can knock out 8 and 24 reduced. So even though they're not right on top of one another, as long as this is a multiplication sign, I could reduce the 8 and the 24 as well. And 8 over 24 reduces to be 1 over 3. So now my numbers are a little bit smaller. 1 times 7 is 7. 25 times 3 is 75. Okay? I know your calculator does a lot of work for you, but I just want to show you some things where if I have to do things without my calculator, it's okay as well. Hey, I'm going to change this one up a little bit here. What's the probability of not yellow? Okay? So we see that word not in here, and you're going to see some ones like this as we go throughout. And so I just want to show you another situation. So how many marbles in that bag are not yellow? Okay. We got 4 yellow ones, so that means 21 out of the 25 are not yellow. Okay? And I want both of them to be not yellow. So I'm going to reach in again. This time there's 20 marbles left out of 24. Okay, what's that give us? Okay. 7 over how much? 10. Okay. Okay, pretty good, pretty likely that that would happen because not yellow means any color besides yellow would be considered a success. And so we have a lot of marbles in that bag that are not yellow. All right, this one probably the hardest one of the group today. Last couple that we're going to talk about. We kind of did one like this yesterday. You got to make yourself a Venn diagram here because we got to be able to break this up. So this is where kind of ties in what we did yesterday and the day before with Venn diagrams to kind of come up with the probability of this happening. Okay, and there's a lot of words going on here, and it makes this problem pretty difficult to do because we got to be able to kind of decipher what's going on and take the information out of there that we need. After the completion of a race, 75 runners asked if they ran a personal best time and if they trained for the race. They were asked that question. Of those surveyed, 22 said that they ran a personal best time, 46 said that they trained for the race. Of those that said they had a personal best time, 18 trained for the race. Okay? There's all kinds of stuff going on in there. And so what we're going to do here is basically the runners were asked 2 questions. Okay? Did they run a personal best time? And did you train for the race? Right? I can't really imagine what kind of race people wouldn't train for, but some said no, I guess. So we always, when we do these, we always work inside out. And so of those that said they had a personal best time, 18 said that they trained. Okay, so that's going to be my inside number. 18 goes inside. "22 people said they had a personal best time. So this whole circle has to be 22. So how many are going to go in the other part of that? 4, right? Because 18 and 4 has to add up to be 22. Okay, same thing for trainers. 46 people said that they trained for the race. 18 of them also had a personal best time, so I take 46 minus 18, and I get, 28, not 26. 46 minus 18. Okay, and you have to do that to kind of figure out what goes where, okay? And then we could also figure out how many did not train if we have to do that as well, or have a personal best time. If we look at the questions being asked, first question says, what's the probability that both runners trained for the race but did not run a personal best time? Okay, so first of all, how many runners are we talking about? 75. Out of those 75, how many trained for the race? That means they're in this circle, but did not run a personal best time. So we're not looking at those 18. So we're only looking at 28. Okay, that's why the Venn diagram is extremely important here. Nowhere in the problem does it say 28 people, right? If you don't do a Venn diagram here, you can't really come up with those 28. So 28 fit this. Okay, so I go and interview that person, then I'm going to go and interview somebody else. What the first person says has nothing to do with what the second person says, right? They're 2 totally different people. So now there's 27 out of 74. Okay, my answer here is going to be a little bit larger number. And I think what I got here is that. Okay, let's do one more. A runner had a personal best time and the other runner neither trained nor had a personal best time. Okay, so first up, a personal best time. How many people had a personal best time? 22. So 22 out of 75 had a personal best time. Hey, how many people neither trained or had a personal best time? How are we going to figure out how many people didn't have either one? Yep, 75 minus this group right here. Okay, and so if we do 75 minus those three numbers there, that would leave us 25. And there's only 74 people left to choose from because we've already interviewed one. Now there's only 74 people left. Okay. So reading these is, and that's what makes some of these kind of hard, right? You got to read, you got to interpret, and then you got to be able to figure out what are we looking at. And I think what I got here is lots of ones. Everybody agree with that number? Does that look right? Is that what you guys got? Okay. 11 out of 111. Okay. Compound probability. Homework 4 is what we got today. This would be the third page in your packets. Probably the easiest way is just to go through and circle these problems. These are the ones I want you to do. So, I mean, you could list them out, or you could just go through and circle them on your paper if you want.
Is that add or odd?
Odd, yeah. 1 through 7 odd. So that just means 1, 3, 5, and 7.